Let's take up a problem on axial loading, and this again will be a problem on thermal stresses. Okay, so the problem goes like this. So there is a steel tube and there is a copper rod. Okay, so like this. So the copper rod is inside the steel tube. The diameter of the steel tube, the outside and inside, are given. Similarly, the diameter of the copper tube is given, and both of them are rigidly fixed at the ends through these rigid end plates. That means they cannot um, move away from each other's end surfaces. Okay, and similarly, the material properties are given for steel plate and for the copper plate. Yeah, steel tube and the copper rod. And the thermal expansion coefficients are given for both copper and steel. And it is known that the when it was assembled, then the temperature was 10 degrees centigrade, and both the rod and the steel tube, they were free of any stress. But now for some reason the temperature has increased from this 10 degrees centigrade to 200 degrees centigrade, and we are supposed to figure out what are the stresses that exist now in the copper tube and in the steel copper rod and in the steel tube. So that's the problem. Now, for such problems, as usual, what we should do, okay, I'll copy this part. We should think in terms of free expansion, in the sense that if one of the rigid end, the backing, was not there, then what would have been the expansions, okay, for both the rod and the tube. Now suppose this end this end plate is not there. Fine. Now what? Then this you see here the copper's thermal expansion coefficient is more than steel, so obviously that would have extended more. Now to show that, suppose that would have extended by this much. This is an exaggerated view. I'm just making some space so that we can put some writings. Okay, and now and then at the same time, because the temperature is anyway increasing, the steel also would have extended say up to this point, maybe a little bit less, but yeah, it would have come, say, here up to this point. Fine. So that would have been the position of the steel. Now, but because there is a rigid end plate, so they cannot have two endpoints, separate endpoints, so they will be somewhere here. Now you see here I am intuitively putting this distance smaller than this distance. Why? Because copper is a bit softer in that sense. See, it is only 100,000 Newton per millimeter square, so it is softer. So this rigid plate would be pushing this rod easily than the other one. Okay. So from that sense, so we will say that the final position of both of them would be this. So that means if you consider the strain, so both of them have got this deflection. Let's call this delta. So this delta over this L, whatever the initial length was, so that would be the strain in both the tube and the rod. But the strain would not be only because of the force that is acting, but also due to the thermal effects. So these are the two concepts which we will use to solve the problem. First, the forces are same. Okay, forces are same. And second, the strains total, I'm writing it total to just remind ourselves that this total will include both the thermal strain plus the strain due to the forces, are equal in both the rod and the tube. Fine. Now, so let's use the first of them. So what will be the force in say the steel tube? Let's say let's say the stress in the steel tube is sigma st, that times the area, so pi over 4, this is this 2.4 square minus 1.8 square. Fine. So this is the force that exists, and then this is a pull force on steel. This is the pull that is coming from this end plate on the on that steel tube. It is pulling, right? And so that should be equal to the sigma of copper times its area, which is pi over 4, it's 1.5 square, and this is also in a way you can say pull, but so this end plate is pulling on this side, but I'll write in a way push because it is compressing the rod. Okay, push force on the copper rod. Okay, so they must be equal. So from here, if you put the values, you should get the relation between them, that is sigma of copper would be around 1.12 times that of sigma of steel, right? Now so that's relation number 1 that we got from the force balance. Fine. Then let's do the equality of strain. We'll write the equation for that. Now that contains two parts. First is, let's say the strain thermal. I'll write say thermal of say copper and see this thermal strain would have come up to this point. Say this would have been the thermal. Suppose this is delta copper. This delta copper over L would have been the thermal strain, but then this has been compressed by this amount now. Okay, so minus and because of so what will be the strain due to that? So this sigma copper divided by E of copper. So that is the strain, right? Now this has to be equal to thermal strain of steel plus sigma of steel over E of steel. Fine. So this thermal strain was this one. Suppose this was delta St. So delta St over L would be the thermal strain, but then it is again pulled by this amount. So this is that. So then here you can apply say alpha copper. Sorry, this is copper times delta T minus sigma copper over E copper is equal to alpha of steel times delta T. This is same for both. And how much is this delta T? Okay, so delta T would be equal to 200 minus 10, which is equal to 190 degrees centigrade. So that is same in both the cases. Divide by sigma of steel over E of steel. So this is another equation which we got. You see here, this is known, this is a known quantity, this is a known quantity, this known, known, and known. Only thing which are not known are this and this. Here this plus this. So there are two unknown. We have two equations, so we can solve them to get the values of sigma. Sigma steel would come out to be 83.3 Newton per millimeter square, and sigma copper would come out to be 93.3 Newton per millimeter square. Okay. So this is how you need to solve the problems on thermal stresses. So we shall meet with another problem in the next video. Thank you for watching.